Okay. So thank you very much, and I will try to gain a little bit of time. So my talk is about rather not very recent, I would say, work, but it is a work. It work concerns the XYZ model, and the XYZ model is one of the most ingenious results by Professor Baxter, and that's why I thought that it would be nice to kind of to uh, talk about this work here. And so, as I said, so it's not very recent, but so at the end I will ask some questions which are still not answered for this model. So we are talking about XYZ model. So the Hamiltonian is written here. So I sum from minus infinity to infinity, but this is okay. So this can be explained. What do I mean? And so there are three coupling constants. There are three coefficients here, and so they're parameterized by the coupling constant nu and the elliptic module tau. So the explicit formula will be written later. And so then the problem which we want to address is that to compute the expectation values of local operators, namely if you have an operator which is concentrated on the part of the lattice. So then we want to compute its expectation values on the vacuum, so in infinite volume. So the computation is based, so it includes several objects. So one is, we begin with the partition function. Partition function is a result of Baxter. So it looks like that. And so, and then using this function, we define three functions, omega 1, omega 2, omega 3. And so the correlation function, this formula for the correlation function for this operator omega, by the way, omega is an operator acting on operators. By this, for this operator omega will be given using these three functions. And so, and also some algebraic construction, but this algebraic construction, so it's only elliptic functions will be involved. So, and from that point of view, so we will see that it's really algebraic. So, and I would say that at the time when these formulas were obtained, so it was kind of nice surprise for us that it is possible, because so before that, so there was some formula for correlation function for XYZ model, but they included some multiple integrals which are rather hard or mostly or impossible to handle. So here everything is reduced to computation. So all the non-trivial transcendental part is reduced to computation of these three functions. So the key to the solution of to our construction is the Sklenin algebra. Sklenin algebra is a algebra with quadratic algebra with 4 generators, and so the commutation relations are given here with constants, structural constants JBC, which are given by theta functions. The theta functions are defined, so the indices of theta functions are, as usual, modulo 4. And so these are kind of traditional theta functions, or I don't know what is traditional here, but so another way is so to use a theta function to count theta functions by half periods in two directions. So it is like written here, and so both ways of parameterization are useful. And so the structural constants, they satisfy a kind of Jacobi identity, which is probably the most important thing here. And then there are two quadratic Casimirs, as we know, so K0 and K2, so they're written here. So, and so then the rest is based on the R matrix. So R matrix belongs to the tensor. So here we consider R matrix, which is uh, which has two spaces. This is called auxiliary, and this is quantum. Yes, and so the auxiliary space can be is just an element of our Euclidean algebra, so A. And so, but these are just sigma matrices. So, and for it should be said that we have finite dimensional representation. I don't write the formula for finite dimensional representations of Euclidean algebra, but so there are formulas for finite dimensional representations. And on finite dimensional representations, the Casimirs, they take these values. So, and what we will need for our construction is the trace. So it is an analytical continuation of the trace for finite dimensional representations, analytical continuation with respect to the dimension. So, and it satisfies several properties. So first of all, when we restrict to finite dimensional representation, so it must be a usual trace. So then, of course, as any trace, it must be cyclic. And then if we multiply an element of algebra by Casimir, of course, so this Casimir goes out of the trace because it's a constant, yes. So, and one more thing is that it is colorless. So, I mean, the trace is zero if if the color of this element is not zero. Color is defined by it was have been already defined. Yes. Okay. So then we defined the commutator or the algebra A prime, which consists of commutators of our generators with any algebra of A. And so the most important result, or probably not the most important, but the important result of our work here is that if we want to, so that the quotient space, so if we, to consider traces, we have to throw away all the commutators, right? And so on the other hand, so the Casimirs are constant. So that's why we are interested in the quotient space of A by A prime. And it is should be considered as a K model. So K model it means that it is created by two Casimirs, K0 and K2. And so the quotient space A over A prime is seven-dimensional. And so it can be realized so as follows, for example. And so you see, so there are only two quadratic elements here, but so because so there are two Casimirs, and so altogether we would have four, but so two of them can be expressed in terms of these two. So this is what does it mean? It means that in principle, so if we compute in order to compute the trace of any element of Sklein algebra, so we can first of all perform some algebraic procedure, and so it is the theorem is that the result of this algebraic procedure is to reduce it to these 7 elements. So so the coefficients will be given by this k0 and k2. And so, in fact, so we have to compute traces only for these 7 elements to know all the traces in principle. So now, the rest of the construction is that we construct the adjoint monodromy matrix first of all. So we take this R matrix, which is in the tensor product of anything with two-dimensional, yes, and act on these operators, local operators, which are something like that, yes. So they are stable at plus and minus infinity, and then something whatever it is in the middle. And then we define the following operator which acts. So this must be O. I'm sorry, I tried to avoid this. This must be O. So operators which act on local operators like that. So it basically consists of a joint action of the monodromy matrix in with the with auxiliary space being the Sklein algebra, and another couple of monodromy matrices where the auxiliary space is just two-dimensional, and trace is taken over the space of this dimension in the Sklein algebra, and B is something given by these theta functions, and then this y I split it into 3 parts: y1, y2, and y3, and the result for this function, for the computation of the correlation function, is that I had this e to omega applied to a local operator, so omega is given here. So it consists of this three transcendental functions, then these coefficients which have algebraic construction as I explained, and then so these integrals are around 0, so I could write residues. Sorry? So, and in this formula it is clear that functions omega are functions omega are analytical, so are regular at the point mu1, mu2 equal to 0. So that's why here I can replace this y by y1 by y, etc., by sy, which means s is a singular part of y. And this singular part of y, it satisfies remarkable properties, because first of all, if I apply to some local operator this SYP, it belongs to, and this local operator has some support, as I had a picture, yes, it belongs to support of O. So then this operators commute, and finally they are nilpotent. So which means that if I take product of this number of them, so and apply it to all, the result is empty space. So in fact, these are properties which we are used to very much in XXZ case, and so they in XXZ case they are explained by the fact that these operators Y are actually quadratic form of some fermionic annihilation operator. So I will return to this. So now let me discuss these results. So first of all, there is a problem with application of these results because so in this formula for Y, this trace over Sklyanin algebra is present, yes, and so in order to compute, say, if we take an operator with length L, in order to compute this trace, we have to compute such a traces for generators of Sklyanin algebra. And as I said, there is a theorem that any element of Sklyanin algebra with using this procedure, taking commutators and Casimirs, so can be reduced to our 7 elements. But unfortunately, this procedure, for the moment, we cannot this procedure algorithmic, so we don't know. So of course, so we did something on the computer, and so we computed the correlation function, say for up to three sites. But so in general, so the procedure of this for this reduction is unknown, and so this is one of those things which make me rather unhappy and prevent me from sleeping from time to time in the night. So then, but on the other hand, so if you the formula which I wrote before is complicated even for XXZ case. It's hard to apply them it's not hard, but it takes a lot of computer power to apply them. And so, but in XXZ case, so we have found a way around this difficulty. Namely, we were able to compute this, to write some formula for this correlation functions. So with arbitrary on a cylinder with arbitrary Matsubara space, namely, so you see, so this is if you take here all there are spins and inhomogeneities here. If you take homogeneous thing here and all spins is 1/2, and then the radius of cylinder goes to infinity, then you obtain the model on infinite lattice. But so you see there are many parameters here in principle, and we were able to compute the correlation functions for these parameters, and then using this, it is possible to write so we have this our fermionic basis, and it is possible to write the expression of any local operators in terms of fermionic basis, and then use it for any Matsubara space we have. So, and this, I think, is more promising direction than computing of even okay, the computing of traces is interesting by itself, but this is more interesting, I think, possibility. But for the moment, we don't know it requires knowledge of creation of operators, because so these guys here, this Y's, so or SY's, they are. I don't go into details, but they are essentially annihilation operators for us. And so to find kind of creation operators to compute this partition functions, and so to do to fulfill the entire program for XYZ case. Is it doable or not? I don't know, but what I know for sure is that probably it is for younger generation to do this if somebody is interested. So with this, I finish my talk. Thank you very much.
Thank you very much.